Right, so today we'll talk about the fifth lecture. We will talk about statistical estimation. If we have time, we'll also address a little bit about hypothesis testing. But before that, let me walk you through the data changes that I was making. So I was trying to put all the data files that the exercises that we have done in the previous lectures into one single data file. And then any future lectures, if we use the same data, I'll just keep add spreadsheet data sheets within that data file. So I'll show you the latest data file that I have shared with you. You should be able to find it on Microsoft Teams as well as the Dropbox. So here's the data file. The name of the data is Lecture105, data COVID-19, June 4th. So yesterday I sent you the data is June 3rd, and this one is June 4th. There's a new spreadsheet in there, in June 4th. So you can see that I'm just gonna walk you through the different, so at the bottom you see different tabs. The first one is just the original data, and the second one is what we did in lecture 2. And there's the data for lecture 2, and there's a step-by-step guide. So remember in lecture 2, we first did a histogram. Just found a typo here, histogram. And here's the step-by-step guide, and there's the pivot table that was used for the histogram. And there's the histogram itself, so you can follow the steps and make the histogram on your own. There's how to make a group box plot, and here's the box plot. And there's also a scatter plot that we did. So this is what we did in lecture 2. So you see what I mean? Like each lectures, each sheet, data sheet, represent a task. So in lecture 4, we did a labeled scatter plot. Again, here's the data for that. They all came from the first tab, like they all come from the data on the May the 30th, COVID-19 data. And here's a step-by-step guide on how to make this labeled scatter plot, and this is what we have made in the previous lecture. Okay, so we also did a little bit of sampling exercise, so you can find here lecture 4 sampling exercise. And there's the introduction. Basically, it gives you an idea of what we actually did, so you can make sense of what the numbers here are. And yeah, so that's that. So this should be, I hope this is helpful for you to track what we have been doing in these lectures, and also the outcomes. So in lecture 5, you can see there are 2 tabs in this data file. There's a centering data exercise. There's also confidence interval. So this is from the confidence interval is from a different data set. Actually, this is not a data set at all. This is a report of some kind of survey that they did by the Office for National Statistics that I will walk you through later. But right now, let's look at this centering data exercise, right? So remember last time we mentioned that you can make a let me go to this scatter plot. The scatter plot, in this scatter plot, what we were doing is to plot, is to see the relationship between population density and cumulative rate of infection. And we decided to do that by different regions. We did that for 3 regions. And you can see the dots for different, from the lower tier local authorities from different regions are labeled with different colors. The orange is from East of England, blues are from East Midland, grays are from London. We're interested in how this relationship differ by region. So as you can see that we have asked for a linear trend lines for each region, okay, as indicated on the legends to the right. We can also see that for London, the there are two trend lines. One is a linear relationship. The other depicts a curvilinear, or as they call it, a quadratic polynomial relationship with x squared as predictors, okay, and x. So that's what I mean by polynomial. And the r squared, as we talked last time, indicates the amount of variance in the dependent variable, in this case is cumulative rate, explained by the independent variable, in this case population density. You can see that this is the linear trend, and you can see the r squared for the linear trend. I'm going to zoom in a bit further. Is 0.03, which means 3% of variance in y is being explained by x, given the linear model. And we can also see that the r squared is much higher, almost 17.6% of the variance has been explained by the polynomial function that include squared x. In this case, what it just shows that is that the curvilinear relationship is fits the data better than a linear relationship. So, and judged by the shape of this trend line, you can see that it seems like the infection rate was increasing as population density increased to a certain point, that it started to decrease. So the increase of population density after a certain point actually decreases with the cumulative rate. Okay, so that's interesting. That's something that we didn't really get to find in the other regions. Well, at least I haven't even tried to fit different regions with different types of trend lines yet. So it is perhaps that for East Midland, you can a polynomial trend line would actually fits better than a linear trend line. Yeah, that's also possible. Right? So the point is that the relationship between these two variables seems to differ by region, and also the shape of relationship also differ by region. Right? So and also in this case, the region is a moderator, is a moderating variable that modulates the type and the intensity of the relationship between population density and accumulated rate. We also talk about what does these numbers mean. So let me zoom in again. So zoom in on one of these, that'll be easier. So given this equation here, y equals 0.017x time plus 207.32. The first number right next to x is the slope, indicates that a unit of change in x leads to 0.017 unit of change in y. And the 207 is the intercept, which means when the x is 0, y equals 207.32. But in this case, x equals 0 has very little realistic significance because you can't have a population density equals 0. So what we talked about earlier is that it would be much meaningful to know what is the value of y when x is the average, is the mean. Right? And not only just the mean of the whole UK, England, but the mean in each region. So what we are trying to do in this little exercise in lecture 5, I'm going to switch over to lecture 5 data. What we're trying to do here is to group mean center the density data. Right? So what we're trying to do is we're going to, so for the density, remember, is an independent variable, and it's predicting, we're trying to predict the case rate. So by group mean center, basically what we mean is that we're going to process this original density data to subtract the average for each region from this original data, right? So in this case, you can see that if I have a density, this is in East Midlands, And for one of the local authorities, the density is 3,299. What we're doing that is converting this value by centering it around the average for the mean for this particular region, which I've written here. So also we know that the mean is actually 187. So we will be just subtracting 187 from 3,299. And that gives, is that the mean? Oh, that's the mean case rate, sorry. So if the mean is, I don't know what exactly the mean density is, but you can see from the equation that it is minus average of I2 to 41, which indicates the average up to 41, which is for the first region, right? So for your, to make it easier, I use different colors to indicate observations from different regions. So for the second region, I also did that, but now we're centering it around the mean of this region, which is east of England. Right? So for local authorities from each regions, I have centered, okay, their density data. Again, this is the independent variable according to the mean, the group mean. Okay. And then I've created, again, the same kind of type of labeled histogram for the first three regions, East Midlands, East of England, and London. Now, as you can see, instead of going from, in the previous scatter plot, it goes from 0 to 10,000. This scatter plot has dots scattering around 0, right? So now the 0 here is really because it has been centered around group means. So this indicates that for each of the regions, you have some data points to the left of 0 and some dots to the right of 0. Okay. And now, if you take a look at the equation, for example, this is the equation. I'll zoom it in. This is the equation for, again, orange line, which is East Midlands. You notice that the slope hasn't been changed, hasn't been affected by the centering. Okay, but now the intercept has changed to 226.08. And if you look at the previous intercept, it is 207.32, right? So this is the previous, this is before centering, right? The intercept is 207.32. And this is after centering, the intercept now has changed to 206.08. Now, as I said earlier, if you center it around the group means of x, then the value of the intercept, which is the value of y when x is 0, is now the rate of infection when the group, for the entire region, right? The average rate of infection for the region. And we can check that, right? So these are the actual numbers. Oh, by the way, that the orange line is for the east of England. Is that the case? Yeah, I think that the orange line is for the east of England. Yeah, east of England, not East Midland. So these are, again, these are the actual average that I calculated, as you can see from the equation here. That's the equation that I used to actually calculate the mean case rate. Okay, that's the dependent variable by regions. Again, this is a dependent variable, not an independent variable. As you can see, that's the same value, 226, and this is the 226.08. It's exactly the same value. Right? So again, when you have centered the x, when you have group centered the x, then the intercept becomes the group mean for y. Okay. So now that's more meaningful. Like now we know that what is the rate of infection when x is at the mean, the average for the region. You can notice that this only applies for the intercept for linear model. Okay, so again, these are the two equations that they got for London. And you can see that these two intercepts are different. One is 324, the other is 296. So which one is the mean? Which one represent the mean y? Y is the infection rate in London, right? So we can check the actual infection rate in London. We notice that the mean is actually 296.46, which is the intercept for the linear equation, not the curved linear equation. Okay? So that only applies when the equation or the trend line that you're adding is linear. It doesn't apply when it's curved linear. Okay? All right, I hope that makes sense. So this is what we call centering, right? This is what we call group mean centering. And that changes, you can see that centering changes the intercept for these linear equations, but not everything else remains unchanged. The slope, the R squares are all the same before and after you center these values. So feel free to go through this on your own. If you want, you can see how the centering is done. I wish that I could find an easier way to do the centering. It doesn't have to be, I don't have, I had to, well, include exact indexes for these to calculate the average. But in the other statistics software, there are easier ways of do the group mean centering. But this is a neat illustration, actually. This wasn't, because the Excel has these equations available. It's actually quite a neat way to actually see how centering changes the regression equation that you're getting. Okay? So that's that. So yeah, feel free to go through this little exercise on your own. Going back to our main topic. Okay, so before we go into the point estimation, let's just have an overview of what we've learned so far. We've learned that data production involves sampling from the population. And then we learned that we can do some exploratory data analysis on the data we have obtained from the sample. We can do that by depicting and summarizing a single variable, or doing that on two or more variables, as we just did in that scatter plot that involves three different variables, X, Y, and region. But it's important to keep in mind that all these summaries that we are doing only apply to the sample data. So we're not really making any inference by just describing what's going on in the sample. We're not really making any inference. By the way, that should be inference. I was saying inference before. Had to Google it, and it turned out to be inference. That's actually much easier to pronounce, inference. To make inference about the larger population from which the data was obtained, right? So in order to do that inference, we need to utilize something called some tool called probability. Right? So probability allows us to make inference from the sample to the population. And by what we are actually trying to do is to use observed values from the sample, such as sample mean, sample standard deviation, to estimate the population parameters. Now, the first thing that we want to make sure that what's in the sample can be also can be also applied to what's in the population is that we need to have unbiased sampling. And unbiased sampling, as we talked before, usually involves some kind of randomization. So randomization actually have two different purposes, serves two purposes. And first, as we show that if the sampling is random, then the sample estimations are, the sample statistics provide unbiased estimation of the population parameters, meaning that in the long run, the average of these sample statistics will approach. the population parameter. The other thing about randomization is that it enables us to use probability as a tool for inference. Okay, because laws of probability basically deal with random variables. So if the sampling is random, then we can use probability for inference. There are two types of sampling. I wasn't really clear about this in the previous lecture, so let me just make it more clear here. There's probability sampling and non-probability sampling. Probability sampling simply means that the method based on some kind of theories of probability. So because it's based on the theories of probability, it usually involves randomization process at some stages of the sampling procedure. So as a result, each element in the population would have a known probability of being selected. So this probability of being selected can be modeled and calculated a priori on an a priori basis. So if this is the case, then we could use probability tools to make statistical inference. The non-probability sampling really is that any sampling method that's not based on any theories of probability. So in this case, it is usually that there's no intention to make any kind of statistical inference from sample to the population. Instead, people are usually only interested in these specific cases being studied, as in a lot of qualitative research design. We talked about probability as understanding the behavior of random variables, and random in the case that the value of the variable depends on some sort of random phenomenon. The concept of probability distribution was repeatedly brought up. It really just shows that using a density function, we can understand the distribution of a probability and the probability of the variable taking a certain range of values. For example, in this case, in a standard normal distribution, we can easily determine probability if we only know the z-score value, right? And then we can determine the probability of a z-score smaller than a certain value or between two values or larger than an extreme value. There are other types of distributions that we have mentioned. They can all be used to determine probability in the same way that we just did with the standard normal distribution. There's t-distribution, there's different chi-square distribution and f distributions. And although the distributions are, the shapes are different and the determinants of these shapes are different, they can be used in a very similar way, that is based on the area, size of the area that's cut off by critical value. You can determine the probability by measuring that. Someone asked what determines whether or not something is random. That's actually such a very big question. Well, there's usually some kind of a random device. You can think of a dice, right? If you roll dice, the dice itself is a random device. So what's really the question is now, in a lot of these natural phenomena, what are these random devices, right? For human, for, I don't know, like for a height, weight, or skin color, or these kind of traits, there's the DNA, right? There's the genes. So to what extent the genes are stable and to what extent the gene can randomly mutate, that is the question for biologists to figure out, right? And in physics, there's probably the movement of atoms, like is usually considered random, right? And so what is really saying here is that if you have a measurement of a natural phenomenon, saying that whether it be in height, weight, related to human or related to some kind of physical phenomenon, there is usually what's called a signal and noise, right? So so the signal is what you expect the true value is, and the noise is just random error, and the part that fluctuates. Okay, that's another way of looking at randomness, is to consider randomness as noise. And you can see that a lot of the times these noises or random variations can be actually modeled, fit into a how do I say that, statistical models of randomness. Okay? So you can observe it and then see how the actual distribution of these phenomena fit in, how well do they fit into these statistical models, such as standard normal distribution, for example, right? So I guess the short question to that is that there are two things. One is that you can empirically observe that something actually fits that definition of randomness, right? And the other is that you can also theoretically determine that by observing what exactly is the mechanism that determines the score, like whether it be the rolling of dice or the DNA, right? So that's that. But very good question. And we also talk about central limit theorem. What it's saying is that as long as you have a large enough sample size, the sample means the distribution of the sample means will approximately be normal, regardless of the distribution of the population. So in the illustration, we show that a very highly abnormal population, when you draw a large enough sample, which is usually larger than 30, then the sample means will actually fit the random, the normal distribution. The implication of that is that we can just apply the standard deviation rules of what we know about normal distribution to determine the probabilities of obtaining certain sample means. So, and that's the depiction of the standard deviation rule. So an example here, if you have annual salary of 54,000, standard deviation of 5,000, and it's normally distributed, that's our assumption about the population. We can determine the probability of a single teacher, right, with a certain value. We can also determine the probability of a random sample of 100 teachers, of sample size n, in this case 100. And we can also determine the probability of the sample mean. Okay, so in this case, we want to determine what's the likelihood of the sample mean to be higher than 55,000. Remember that the first question is about a single value. It's equivalent to a sample mean for a sample of 1. The second question is about how the sample means. So it's about given a sample size of n. So this is the first question can be answered by this model, right? So we know that if we took a single value, this is the distribution, and we have a standard deviation of 5,000 in this case, and we can determine the location of the critical value on this distribution, and we'll be able to determine probability like that. But a sample mean distribution takes the same shape, but now the standard deviation is much smaller. So it's 5,000 divided by square root of 100 is 500, right? So it's the same shape, but now you can see that at +2 standard deviation is 55,000 for the sample means, instead of 59,000 for the, actually instead of 64,000 for the population, right? So if you have a large enough sample, then your sample mean distribution will be have a much smaller spread than the population, as we discussed, right? So yeah, and again, we can use z-scores to depict all these by converting any kind of normally distributed random variable into z-scores by first of all centering it. Again, as we talked earlier about centering, and we could also then divide it by the standard deviation. So the two scores can both be converted to the z-scores. We just had to know that the standard deviation for each score is a bit different. For a single score, you basically divide it by the standard deviation of the population. So you can see that the probability of, so 59,000 converts to a z-score of 1 plus 1. And the probability of a z-score larger than plus 1 is about 16%. Now, if we talk about the random sample, then we just have to use the sample standard deviation for the sample means, which is standard error, right? If we have 100, sample size of 100, then the standard error will be 1/10 of the population standard deviation, in this case 500. So the z value in this case for 55,000 is plus 2. So the probability of z larger than plus 2, if you look at the z table and convert that into larger than, then you would know that it's about 2.3%. So you can determine the probability of a sample means, okay, larger or smaller than a critical value. And that's something that's to keep in mind when we move on to the point estimation. So yeah, so the reason that we reviewed all these different principles is that we will be drawing on all these principles to accomplish two goals. One, basically we want to draw conclusions about the population. In other words, we want to do some sort of statistical inference. There are some conditions it's for these two types of tasks. As we mentioned earlier, the sample distribution is really much more theoretical. We are assuming in this task, we were assuming that the population parameters are known. And then we try to understand how the sample mean behave around the population parameter. But in reality, which is our task of statistical inference, these population parameters are usually unknown. So we're trying to quantify how precise is our sample mean in terms of estimating this unknown population mean. So there are three forms of inference here. One is point estimation, interval estimation, and hypothesis testing. We'll try to cover the first two, and if we have time, we'll go to hypothesis testing as well. So here's an example of point estimation. Like, we don't know the exact proportion, right, of US registered voters who want to vote for Trump. We conducted a poll of n equals 1,000 American registered voters, and assuming this is a random sample, and found that 53% of them wanted to vote for Trump. I highly doubt this is this number reflects the reality right now, but who knows? So the question being asked about point estimation is what exactly is the exact proportion of all U.S. registered voters who wants to vote for Trump? That's the question of point estimation. And interval estimation is the same kind of question, but now same kind of data. But from this data, we want to ask what is the likely range of proportion? Okay, and we are now we have two things here. The first thing is the likelihood. In this case, we put 95% there. The second thing is it becomes a range of proportion instead of a precise value of proportion. And hypothesis testing now comes a little bit further, that we now have a specific hypothesis that we want to test. So for example, from a previous election or previous poll, we learned that the percentage of proportion of voting for Trump is about 49%. And then the question is that do we have, based on this new evidence that we got that indicates 53%, do we have strong enough evidence to reject our initial hypothesis or not? So we come, in this example, we come with some kind of a hypothesis to begin with, and we are now evaluating our empirical data against this hypothesis. And as you will see, these three are actually strong, connected, as they all utilizes the same kind of tool, but they're slightly different in terms of how they frame the questions being addressed. So the point estimation, if we're dealing with sample mean, or in terms of our voting example, sample proportion, the sample proportion, I forgot to put a hat on top of the sample proportion, but it should really be a p hat. P hat is a point estimate of p. Sample mean is a point estimate of population mean mu. Both are considered as unbiased estimators, so then in the long run distribution is centered at p and mu as long as the sample itself is random. Okay. I saw a question in the chat. I'm just going to quickly look. Is hypothesis testing also to confirm a hypothesis? We'll get to that when we come to hypothesis testing. But in general, you can only reject a hypothesis. We really talk. Okay, so we don't use the language confirm. Usually, you say that based on the evidence, we choose to reject or to accept one hypothesis versus the other. So the phrase confirm should be in general. You should avoid that. You should avoid using that term confirm in any kind of writings. You can say that based on the evidence, what do you choose to reject or what do you choose to accept? Okay, and you will see that when we come to that hypothesis testing bit. Right. So we saw from the sampling distribution, right? That the larger the sample size, the smaller the standard error, which means that the more accurate the point estimator is, that our point estimators are closer to the unknown population mean. We already know that, right? So here are two brief questions just about that. So the first question, based on the survey results, we talk about sampling proportion here. Who use the internet, proportion of US adults who use the internet on a daily basis is 37% or 0.37. This will be unbiased and most accurate if the survey was based on A, a random sample of 1,000 US adults, B, a random sample of 2,500 US adults, C, a random sample of 1,000 college students, or D. So provide your answer in the chat if you just quickly type something into the chat. So what will be both unbiased and most accurate? So in this case, unbiased have two meanings. First of all, it has to be a random sample. The second of all, it has to be unbiased in terms of the question, research question that we are addressing. So if the survey was to try to answer a question about all US adults, then if we sample from college students, then it's a biased sample, right? So we have to sample from US adults. And then a larger sample is more accurate than a smaller sample. So 2,500 will be more accurate than 1,000. So the answer is B, as you have most of all of you have figured out. The second question, a study estimated that the mean number of children per family in the United States is 1.3. So this point estimate will be unbiased and most accurate if it were based on which of the following samples: a random sample of 10,000 US families with children from the state of Utah, a random sample of 500 US families with children, a random sample of 5,000 US families with children, or a random sample of 1,000 US families. So as you can see, there are some of you said D, some of you said C. So let's look at the question a little bit more carefully. So C indicates that you only sample from families with children, and D indicates that you should sample from all families. So so the real what's being estimated here is the mean number of children per family. So should that number be including families without children? That is 0, right? So I think in this case, it should be, right? So the mean average number of children, mean number of children per family in the United States should consider all families with or without children. So in this case, it will be biased to sample from only families with children, and we should also include families without children as well. So in this case, it's been tricky, but the answer should be D. So there's some issues about point estimation that it is very simple and intuitive. It provides a value, provides some kind of certainty. It's like telling people that today's highest temperature is going to be 20 degrees. But it's error prone. It's by definition wrong because it could never be precisely 20 degrees. And so it's error prone. So we all know that sampling error refers to the difference between the sampling statistics and the population parameter. And these errors are just a fact of life for any kinds of point estimates, right? So why don't we try to quantify this estimation error so it gives a little bit more information there. So by quantifying would be two things. We want to quantify the extent of the error. So the extent of the error means how big or small the error is. So we can do that with an interval, right? We can also attach a confidence level about interval. So how confident you are about this estimation. So this brings us to the question, the topic of interval estimation. So what we're trying to do here is that we try to estimate, again, a population parameter using some kind of interval that includes a lower bound and an upper bound. Okay, so a lower bound is a smaller value than the upper bound, and that is likely to contain the true value of the parameter. By the way, this is all about quantitative data here, quantitative variables here. It's not about categorical variables, just in case, okay, you wondered. The likelihood is represented as some kind of a percentage or confidence level that this interval captures the parameter, right? So hence the term confidence interval. So I'll give you an example using a mean, right? So suppose that we're interested in studying the IQ levels of students in a university called Smart University. We have a random sample of 100 students, and what we observe from this sample is that the mean is 115 of IQ. Not so smart because the IQ has an average of 100 and a standard deviation of 10. But the key is that we really don't know what the population parameter mu is in this case. So what we have is the sample. And so based on that, we can make an estimation that I say this, right? I am 95% confident by using this estimate. I'm off by no more than 3 IQ points. In other words, I'm 95% confident that the actual parameter mu, which is the mean value for the entire university, is within 3 of 115 or between 112, which is the lower bound, and 118, which is the higher bound. So now that gives us more information to work with, gives the reader more information. First of all, there's still the point estimation of 115, but now you give a range that is 3 IQ points below and above the point, right? And you also say that 95% confident. Right? So that gives you a little bit more assurance, because before, like, you don't know like how confident you are. Now you're attaching the confidence score into with this interval. So this is how it is constructed. So if a random sample of size n, right, is taken from a normal population for a quantitative variable whose mu is unknown, and if we know the population standard deviation, which in this case is a sigma, and a 95% confidence interval for mu is plus and minus x bar, which is the sample mean, plus and minus 2. Okay, here I'm using 2 because I just copy pasted this from the statistical learning course. The exact value should be 1.96, right? Let's, if you want to be more precise here, times what standard deviation divided by square root of n, which you know that is the standard error, right? So this, what exactly means is that 95% of the time, this interval would actually include mu, and 5% of the time, the interval will miss mu, okay? So, and also, we're talking about when the population standard deviation is known. When we don't know that, we just use the sample standard deviation as an unbiased estimate for the population standard deviation. But it's still square root of n when you calculate the standard error. So I said it should be n minus 1. That was wrong. It should be still square root of n. Basically, if you only know the standard deviation of the sample, you divided it by that by square root of sample size, and you get an estimate of the standard error, okay? So before we go on to a break, I just show you a quick visualization. What exactly does it mean to say that 95% of the time the population mean is covered by the interval, right? I just share with you this new, oops. Just want to share with you this new, this little demonstration. Find my Safari window. Just want to show you this because, okay, so what you see on the screen is a simulation of 95 confidence interval. So again, this is a population distribution. We have a population being mu here, and we have some buttons that we can press, right? So you can sample one. You can have one sample, and this is one sample. And I'm not sure about the sample size, but let's say that we have one sample, and then it has, this is this estimation of confidence interval, and it's 95% confidence interval. So covers from left of this line to the right of the line. And you can see the red dot indicates the sample mean. So if you have one sample, you get this, right? You have another sample, you have sample mean, there's another sample, you have a different confidence interval. Now this time they move towards the left of mu, and this is the sample mean. So again, we're estimating, this line estimates 95% confidence interval. So if we just sample 50 times, right? We have sampled 50 times. You can see sometimes we draw a sample that's a bit more extreme, that the confidence interval will miss mu. Again, this is 95% confidence interval, okay? So if we draw a very extreme samples, that's just by sheer luck, bad luck, that we draw a sample that's so extreme that the confidence interval based on that particular sample will actually miss the mu. Okay, in this case, we made some kind of a error, right? It was a mistake, but it was a mistake caused by random chance. So in the other cases, you can see, although the sample means deviates from the population mean left to right, but their 95% confidence interval still covers the population mean mu. So in this case, we have, if you read the numbers here, we have simulated 50 samples. We have 47 hits, which is 94%. So that's our empirical probability, which is 94% of the time, which is pretty close to 95, right? We sample another 50. Now we have a perfect 95% empirical probability. So if we can sample it more or less, but in the long run, it's going to approach 95%, okay? So that's what 95% confidence interval means, right? So if we don't know mu, and if we happen to like 5% of the time, our estimation of mu is going to miss the actual mu. So on that note, let's take a break and come back at 2. Okay, I'm going to pause recording. And so yeah, so in the previous illustration, we see that what exactly does it mean, right? So if we, again, in this case, assuming the mu is known, we see that 5% of the time, the 95% confidence interval will actually miss the mu. So here's the general equation for confidence interval. To the left is the equation that I showed you earlier, which is 2 times, yeah. But that 2 is actually is called a Z. The Z is the confidence multiplier. We get to that bit later, right? Because you can attach not just 95% confidence to that. You can have different levels of confidence. And again, if you wonder if this has to do with standard deviation rules or Z distribution, yes. So the whole part where Z times this is called the margin of error. Okay, so this plus and minus, the value after plus and minus, is called margin of error. So the X bar is the point estimator. In this case, is for the mean. But you can have a you can have a confidence interval for other samplings, other parameters such as standard deviation as well. Okay, so this point estimator does not have to be mean, but it can be applied to any kind of statistics that you are using. After that is the standard deviation of the point estimator. Okay, so the margin of error equals confidence multiplier multiplied by standard deviation of the point estimator. Again, when we don't know the population standard deviation, we use sample standard deviation as a point estimate, putting the position of sigma. Also, this multiplier, even in the case of a sample mean, it is not always a Z value. For example, when n is smaller than 30, you can still have a confidence interval, but you have a t-score as the confidence multiplier, and you have a different estimate of standard deviation. So this is what it visualized. So you have margin of error above and below the point estimate, and the confidence interval always have a width of 2 margin of error. M here means margin of error. So that's sometimes it's kind of confusing to read the results of political polls, for example, to tell you what the margin of error is, right? So you would know that the margin of error actually means half of the confidence interval. You can attach other levels of confidence to the confidence interval, and as you might have guessed, well, it might not be obvious. So like let's just go over it. Like for 90% level of confidence, the Z value equals 1.65. 95% is 1.96. 99% is 2.576. Okay? So what this suggests is that as the confidence level increases, when everything else remains, all the other factors remain unchanged. That is, the standard deviation is unchanged, and unchanged, the sample mean is unchanged. The more confidence it is, the larger the confidence multiplier, indicating the margin of error also becomes larger. Okay, so it is so this is a trade between how precise is your estimation and how confident is your estimation. And we'll do a, so this is again an indicator. So if we are estimating the IQ of the entire university, 99% confidence interval is from 111 to 119, which, as you can see, is less precise, right? It will provide a larger range. But the confidence is not increased to 99%. You can say 100% is going to be from 0 to like infinity, but that doesn't give us any kind of information. But now you can say with 99% confidence, it's actually within you could give it an interval of 8, which is not bad. But if we are willing to reduce that into 95%, then you further narrow it down to an interval of 6, right? So there's a trade-off between confidence and precision, which indicated by how the width of the interval. To show you that, I'll have another simulation. So bear in mind as I take out my Safari. So I can show you the other simulation of different confidence intervals. Okay. So here on the screen is another simulation that I have. You can see that different from the previous simulation, we can specify different confidence level. You can select from 80%, 90% to 99%. Let's just quickly reset it. First of all, let's see that the definition of confidence interval indicates that for 80% confidence interval, it's going to miss the mu 20% of the time, right? So let's specify 80% and sample 50 times from this population and see whether that's the case. So here you can see that if we have an 80% confidence interval, which is shorter than 90%, which I'll show you later, the empirical rate, hit rate is only 68% for our first sample of 50. So for our first 50 samples, which is kind of unlucky. Let's just try to do it a few times, increase the total sample numbers of sampling. Now you can see that as we increase the number of sampling, it started to approach 80%, right? So 80% of the time, this 80% confidence interval will include mu. So that's that, right? So, but if we also try to see that the length, the width of confidence interval, we could sample once 80%, which missed, sample another time, and then sample take another sample and calculate 95% confidence interval, right? So next one will be 95% confidence interval. And you can see that 95% confidence interval is much wider than 80% confidence interval, right? So, and then if we increase that to 99% and do another sample, you can also see that 99% confidence interval covers a much wider range than 95% confidence interval. So to illustrate that a little bit further, let's do 5 sampling of 90%, estimate 95%, and then 95%, 5 times, 2, 3, 4, 5. 99%, 1, 2, 3, 4, 5. You can see that, oh, it's not quite clear here because our sample goes all over the place. But you get the idea, right? So so as you increase in terms of confidence level, your estimation becomes less precise in that the width becomes larger, okay? So it becomes wider and wider. And that's assuming everything else is kept constant, kept unchanged. Okay? Okay. Let's talk again about the proportion because that's quite interesting, and that's being used in especially political polls a lot. So remember for the proportion, the standard error of sampling of the proportion. I'm saying something in the chat. Or the Mentimeter. I'm gonna. Okay, let me just quickly pause the recording and send you the Mentimeter code. So the sampling proportion has a very interesting. Well, first of proportion is like what's the percentage of people voting for Trump, or percentage of who believe, in this case, who believe marijuana should be legalized. And you have a proportion estimate of 0.56 of a sample size of n equals 1,000. But an interesting case that the standard error it's easier to calculate. So you have a square root of p minus 1 times 1 minus p divided by n. So n is the sample size, p is the population, supposed to be the population proportion. But if you don't know the population proportion, you're using the sample proportion to estimate it. Okay, so the multiplier is z again. So the standard error, or it's the standard deviation of the estimator, right? Because the standard error is the standard deviation of the sample mean. In this case, the sample proportion. Well, that's the formula for the sampling for the standard error of sample proportion. Okay? So that's really the advantage of this is it is quite easy to calculate, right? Once you know the proportion, even just from the sample, you can quickly estimate the population standard deviation and standard error, knowing the sample size. So this method can also have certain assumptions for a sample proportion. First of all, each how to say, like each event, which whether it means that it happens or not happens in the sample, has to be larger than 10. The frequency has to be larger than 10. So you have the second is that the population should be at least 10 times as large as the sample, right? So say if you have, if the proportion is 10%, then you need at least a sample size of 100 to make sure that the sample size times the proportion is larger than 10 for both p and 1 minus p. So let's do a quick exercise on this. I'm going to copy and paste this to you in the chat. Let's say that you run a political pool. So this is an online confidence interval estimator for political pools. So I'm going to put that link on the chat so everybody can see that. So if you open that link, it should be able to show you the sample size calculator, which is on the screen. Okay. So what you can do is a few things. You can first of all, if you can determine that given a certain kind of precision level, you can determine how big of a sample do you need given the confidence level, and well, also affected by the population to a certain extent. You can also find that given a specific sample size, how does the sample size affect the confidence interval, right? So how does changing sample size affect your level of precision? If you want to achieve a certain level of precision, you want to see how, if you want to see how accurate your estimation is. So let's do the first exercise. Is that let's change the assuming a population size of 100,000. We would like to use the find confidence interval tool. First of all, there are two tools. I want you to use the find confidence interval tool for the first exercise. And if you change the sample size from 10 to 200 to 1,000 to 5,000, keeping the confidence interval the same, just try to observe whether the interval is becoming larger or smaller. Again, this confidence interval is it's a little bit misleading because it really just shows how big the interval is, right? So let's go to that. Go to that the tool and do that on the screen, so it's better to illustrate what to do. Okay, so you have two tools here again. Find confidence interval. So if you have a population of 100,000, put it there. That's 100,000. And you have a percentage. Okay, so what exactly is percentage mean? You can click this. So the percentage actually determines the p is the p hat. It's a p, right? So remember the equation is p times 1 minus p. And if you just look into that a little bit more carefully, you will notice that p times 1 minus p is maximized when p is 0.5. So this percentage is just the estimate of the variation inside the population when it's 50-50, when it's 0-1, right? When it's a dichotomous choice, the 50% is the maximum of variation that you can have in the population. Now, to think about that differently, if you have a percentage of 99%, which means, for example, 99% of people would not vote for Trump, then by definition, the variation within the population is very small compared to 50%, where it's maximized, right? If you have only 90%, then it's like the variation is slightly larger than 99%, right? So this percentage here is p, and p. Because p times 1 minus p is the variance, it is maximized when it's 50%. So by keeping it at 50%, you're kind of doing the most conservative kind of estimation for this particular study. And it is the case, like in Brexit, in the general elections, you usually get something that's very, very close to 50%. You don't really get like 70, 30%, 70% that often, right? So 50% is not that too far away from the actual cases for political polls a lot of the time. So what I'd like to do is to start from 10, right? So if you have a sample size of 10, you can calculate, and then you have confidence interval of 31%, which means your estimation will be 15.5% above and below whatever you observed. Right? You say you have 50, you get like 52% in your sample, and that's your confidence interval, right? And then if you increase the sample size to 100, you can already calculate that again. You can notice that increasing from 10 to 100 has decreased the confidence interval from 31% to only 10%, right? So you can see that at the initial stage, when you increase sample size, it actually gains a lot in terms of precision. But as the sample size becomes larger and larger, this kind of gain starts you start to gain less and less. So let's say if you want to increase sample size from 100 to 200, so I enter 200 here, and you calculate, now the confidence interval has decreased, but not by so much, right? From 10 to 100, we decrease it from 31% to 9% to 10% about. And increase from 100 to 200, only decrease it by about 3%. Okay. If we further decrease the increase sample size to 1,000, you can see the confidence interval becomes smaller and smaller. But in this case, we increase it by 800, but it only decreases by about 4%. 1,000 to 5,000, it decreases by about 1.5%. So you can see that there's like the marginal gain that decreases as your sample size increases. The marginal gain increases how precise you are. Right? So it's important to strike some kind of a balance here, that you want to be practical, because a larger sample size means more expensive, more cost. So you want to pick a sample size that gives you the best kind of a confidence interval, but doesn't cost you a fortune to reach. So that's the first exercise, called varying sample size. You could get the confidence interval estimate. The second exercise is called population variance. So remember earlier that the population variance is the highest when the variation is the highest, when it's 50%, when we define 50%. So let's pick a sample size of 200 and a population of 100,000. We want to change the variance with the population, within the population, from 50% to 75% to 99%. Okay, so let's fix that. The sample size we fix at 200. We just clear everything. Sample size 200, population 100,000. When the percentage is 50, we calculate the confidence interval is 6.9%, okay, as we used. So how about we change that to 75? Remember, if we change that to 75%, it decreases the variance. And what exactly does that do? Let's go back to this equation to see what it means to decrease the variance. So to the left-hand side, you see p times 1 times p hat. That's the variance divided by n becomes standard error square root. So if p and 1 minus p, again, we said earlier, it's maximized when p is 0.5. So decreasing the variance basically means that this whole value becomes smaller, right? So the whole value, like the whole, it's not margin of error, it's whole, what is called standard error standard error for p hat will become smaller. So our confidence interval also becomes smaller. And then we get more precise estimation. So let's change that to 75% to see if that's the case. In this case, we change it to 75. You see that the confidence interval has reduced to 6. If we be more extreme, we say 99%, that the confidence interval will become 1.4. And this is also intuitive to understand, because if the variance is really low, which means like 99% of people is going to not vote for Trump, then you don't need that much bigger of a sample in order to achieve the precise estimation, right? Because all the sample you're going to take, you're mostly getting 100% or 99%, right? So it's much easier to get to the actual estimation of this 99%. Again, that's the percentage here, with a smaller sample. And if you have the same kind of a sample size, then it becomes more accurate as the variance within the population becomes smaller, okay? So it becomes much easier to, much more precise. Your estimation will become much more precise. So this is exercise 2 of how population variance influences the confidence interval. So the third exercise, I want you to determine sample size, and that is exactly what the pool, like political pool, like do, right? So usually they want to fix the confidence interval, and they know the population, whether it's a local community, local authority, or the entire country. The population is you kind of get the idea of how many registered voters are there. So for this, I would like you to set the population at 100,000 again. So you can estimate to achieve that 95% confidence interval of 3%. I see somebody raised a question here. This is not a power calculation. It's very different from a power calculation. Well, I will talk about it later. Power is more about how, power is something that's completely different, okay? So, so the third, okay, let me just go back to the tool to show you what it means. So now we're using this determine sample size tool here. We can have the confidence level at 95%, a population 100,000. Okay? So if you want a confidence interval of 3, and again, that 3% means that the margin of error is halved. So it's a margin of error is 1.5% if we have confidence interval of 3%. We can calculate the population, calculate the sample size. So to see that for 100,000, in order to achieve a confidence interval of 3%, which is quite small, you only need 1,056 sample. Okay, this really illustrates the power of statistics, is that you only need a relatively small sample to achieve the high precision. And how about confidence level? If you decrease the confidence level of 80%, we don't have 80% here, but we only have 90%. If we want to decrease the confidence level, then we would need a smaller sample size, right? Okay, this logic here is a little bit more complicated. If we want to increase the confidence level, but keeping everything else unchanged, keep the confidence interval unchanged, okay? Because before I was showing that everything else being equal, how does changing confidence level affect the size of confidence interval? But what I'm doing now is trying to fix the confidence interval by saying we want to be more confident of the same kind of confidence interval, right? And then if we calculate that, we realize that we need a much larger sample size to achieve the exactly same confidence interval, but with a higher confidence level, okay? Again, if we decrease that to 95%, we need a smaller sample. So you can see that if we want to increase confidence level by 4%, everything else being unchanged, we need about 800 more out of 1,000 samples, like 80% increase in terms of sample size to increase confidence level by that much. Okay. The final exercise is the use same determined sample size tool, but we want to see how does that affects, how does population size influences the sample size. Now this exercise really shows us that as long as sample size, as long as the population size has reached a certain level, and as long as we have a certain amount of sample size, then you can achieve the same kind of precision regardless of how big the population is. So the question now is, if you have a population, changing population size, what is the sample size needed to achieve the exact 95% confidence interval of 3%. So clear everything, we have 3%, right? And 95% fixed. So we fix the confidence level, fix confidence interval. Let's change the population, right? So if your population is 10,000, you need 964 the sample size of 964 to achieve the confidence interval of 3%. At 95% confidence level. If you add 2 zeros behind it, if you add 1 0, okay, let's just add 1 0, so it becomes 100,000. You calculate again, the sample size required only increased by about less than 100 when the population has 10-folded. Now let's push that to some extreme. So we have, if we have 100. I think it's 100 million. It's like if you have it's 100 million. If you have 3 zeros add on after that, right? 0, 0, 0. So now you have 100 million people, which is close to the population of UK, a little bit more than that. If you see how many samples needed in order to get a 95% confidence interval of 3%. You'll be surprised you only need about 10 more participants or 10 more in the sample in order to achieve that kind of a confidence interval, the same kind of precision. So it just shows you that as long as the population size really doesn't matter that much to a certain point. So you can have 1,000 participants or 1,000 elements in the sample. You'll be just as precise estimating 100 million estimating a population of 100 million as you would estimating a population of 100,000, right? So as long as this sample is unbiased sample and random sample again and again, that is usually what's difficult, right? But as long as it's a random sample, a sample size of 1,000 can be as powerful for a population of 100,000 as it is for a population of 100 million. But that also illustrates the power of statistics, that you can easily estimate a population of the United Kingdom on some opinions, as long as you have a good enough random sample, which again is the tricky bit. Okay? Okay, so if you want, you can continue that exercise on your own afterwards. Let's just move on to a more practical topic. So I was looking at COVID-19 data, and I noticed that they do this kind of a survey. Office of National Statistics working with Oxford University, UK Biocenter, IQVIA, no idea what that is. Well, acronyms. So they updated this data every few days. I believe today there will be an update, but as of this morning, the 28th of May is still the latest data. So this is quite interesting. You will see a lot of the what we talked about in today's lecture, but you will notice also the things that are a bit different for this particular survey. So I haven't included the whole survey data. I haven't shared it with you in the folders, but here it is on the screen. This is the whole key findings of the survey. I'm just going to go through this survey findings with you. So there's the cover sheet. So I'll share with you after the lecture. So this is the contact details, date of publication, that thing, right? So the content, they have all these spreadsheet. These are contents, and they have done different estimates. As you can see, they have overall estimates of the population in England. Again, this is, why is this thing not going away? For some reason, this little, okay, I see that it is a little bit messed up on, I'm going to share with you I'm going to change the screen share, okay? Excel. Okay, now that should be clear. Oh, not this one, sorry. You share, so. Share. Okay, so that should be clear now. Okay, good. So estimated population in England newly infected per week, percentage of people tested of positive antibodies. You can see a lot of words like estimated, current infected, and also they have estimation by specific groups, estimated percentage of test positive by age bands, sex, health and social care workers versus other individuals, any symptoms in England, cough, fever, loss of taste, smell, England, working location, England. Now, the key word here is really estimated, right? Because we talk about a point estimation and internal estimation, and then they're doing all these estimates. So let's look at what exactly the results look like. They didn't really provide raw data for this, and they didn't really specify exactly some of the method they're using, but still we can use the data for some kind of exploration. So this is table one. I'll zoom in a little bit. So table one is overall estimated percentage of the population. So remember, this is a proportion estimate, right? Population proportion, right? Because it's percentage. This is between 11th of May to 24th of May who are infected for COVID-19. They have tested 18,913 in this survey, right? In this survey, they have that many participants for the survey. Again, I'm a bit surprised they're not using the full everybody who has been tested. So probably they sent out a survey to the household. I don't know, like the analysis. Anyway, they only have like 80,913 in. So that's the end, right? That's the sample. And so I made a note here. So these participants came from 8,799 households. And they only have 36 of them tested positive. So 36 out of 18,913. Okay? So they have this estimated average of the population had COVID-19, but they said weighted, right? So notice that it says unweighted here, and now it says weighted. Now I don't know exactly what this weighted mean, and they didn't really specify that. And see, that's the estimation, 0.24%. That's the point estimation that they made based on this data and some kind of weighting. And that's the lower bound of 95% confidence interval, which is 0.11%. The upper bound is at 0.46%. Based on these, they basically timed this 0.24 with the population of England, right? So that now they provided, using that, they provided the estimated average number of people in England who had COVID-19 weighted is 133,000 between 11th of May to 24th of May. But you can see that they also provided 95% confidence interval that is between 62,000 to 250,000. Now that seems all clear and nice, but let's look at it more carefully. We notice something that's a little bit different from the 95% confidence interval that we talk about today. First of all, if you look at the difference between the lower bound and the upper bound to the mean, you notice is that the difference between the mean as the point estimation to the lower bound is 13%. Right, so I'm just going to note it here, 13%, and then 13%. Well, it's giving me 0. I think it's been rounded up. So I'm just going to format cells to general, so it will show 13%. Just going to give it a percentage. Can I give it a percentage? Yeah, percentage. 13%, right? So that's the difference between not 30, but 0.13%, 0.013. Okay, so like 0.13%, right? And so that's the difference between lower bound and the estimate. But you notice that the upper bound and the estimate, the difference is larger than that. So 0.00022%. Okay, format cells, general, okay. So that's the difference. So this is the margin of error, right? But this is the lower, right? This is margin of error, but this is lower than the estimation, right? Lower margin of error. To the other hand, there's the higher margin of error, upper margin of error. So notice that these two are not the same. So this is different from what we learned today, that if you have a minus and plus the same value, that these two margin of error should be the same. Okay? So I presume that this has something to do with the way that they've calculated the 95% confidence interval. But first of all, there's some kind of a weighting going on. That I will illustrate later that either the 2.94, 0.24% is not really the exact estimate from the data they presented. So there's some kind of a process going on afterwards. And also you can see that the margin of error is also asymmetrical. I presume that this makes sense because what it's saying that is that it is it's less likely to have a lower infection rate of infection than what's the estimated, and it's more likely to have an infection rate that is higher than what's been than the point estimate, what it shows, right? But we can also use the data they provided, simply this data, that is 36 out of 18,913. We could calculate a 95% confidence interval ourselves. So in the second sheet, which I actually included in the other data file that I've included, that I've shared with you, which I'm about to put it on the screen, Just give me a quick moment. Just share this one on the screen. Okay, so this is the data I've shared with you today. You'll notice that to the last sheet is like lecture 5 confidence interval. So this is exactly the data that was shown earlier. Right? So the probability is just that, so now we use our traditional method instead of their method to calculate our 95% confidence interval, okay? So P is the probability observed from the sample. This value is basically 36 divided by, so this value is basically 36 divided by 18,913. Okay, as you can see, that's the value. So remember, 36 tested positive out of 18,913. So that's that. That's our observed P. As you can see, this value is quite small, which indicate the variance existing inside the population is actually quite small. But in this case, even a small variance matters, because when you translate that into the number of people that are affected, then that becomes quite significant, right? Because you have a huge population. So 1 minus P, right? So you want to know 1 minus P, and this is 1 minus P. It's basically 1 minus this value. So this is P times 1 minus P, and this is our sample size N. Have I not shared with you? Yeah, if you like, yes, the last table. Yeah, it's the centering data. Oh yeah? Okay, so I'm gonna share this file with you on chat, so you can just have the data. Perhaps it is possible. Yeah, I have so many versions of the data that I lost track of which ones are which. Quickly pause the recording. The error for sample proportion is the square root of P times 1 minus P divided by N, and that's the standard error. Okay? Now, from standard error to 95% confidence interval is that you have to multiply that by the multiplier. So if it's if it's a standard score, you will use 1.96 for the multiplier. So this is the lower bound. It's just that the point estimation minus the multiplier 1.96 times the standard error, which is whatever value that is in G24. That's the lower bound, right? So using our method, to the right you have the upper bound. So, and the margin of error is just upper bound minus lower bound divided by 2. Okay, so margin of error is just that. Okay, so that's our margin of error. So now our estimation based on our traditional method is the infection rate is between, the rate of infection is actually 0.13% to 0.25%. Right? You can also use the Excel formula to, it's called the confidence norm. Right? So this is the formula that's being displayed on the screen. Let me just drag it a little bit so it can make it easier for you to read this whole formula. It's confidence.norm. You have 3 arguments for this. The first one is the 1 minus the confidence interval. It's called alpha. We will come to that later during hypothesis testing. We'll talk about alpha, what that is. But in this case, all you have to know is the alpha is 1 minus 95%, which is 0.05. The second is the standard deviation. Now, that's not standard error, okay? Standard error is the square root of p times 1 minus p divided by n, when standard deviation is the square root of p times 1 minus p. So the standard deviation of the whole population, that's what it is. It's not a standard deviation of sampling, of the sample proportion. And third is just the sample size. In this case, is this value here. So that gives us margin of error. So confidence.norm function with 3 arguments gives us the margin of error. As you can see, that these two are pretty much the same. I'm pretty sure that it's just a difference in terms of how much rounded digitals. But you can see that based on the calculation using 1.96, it's quite similar to the value we got from using the Excel formula. So on that note, let's take a break and come back at 3 o'clock. And when we come back, we'll talk about more about hypothesis testing. And so here's the by age group. And for each age group, again, this bar indicates the point estimation, and the whiskers indicates 95% confidence interval. So it's the same data that was in that Excel sheet that I haven't shared with you yet. And so that's that. And rolling down, you can see that now, you can see in this case that you can see something that's interesting. You have individuals working in patient-facing roles, individuals not working in those roles. Oops, the cat just jumped on my lap because he wants to be petted. Usually he just goes to sleep. Okay. All right, so if you don't mind. So the individuals working in patient-facing roles, you notice that the confidence interval is much, much bigger, larger than the individual not working in patient-facing roles, right? You can see the confidence interval is much smaller, which means you have a more precise estimation for individual not working in resident phase roles, because presumably you have much larger proportion of those people in the sample, right? So you have larger sample size, so smaller confidence interval. And for this one, you have a smaller sample size and larger confidence interval. And based on this, they said that the difference seems to be significant. So there's a difference in terms of percentage of individuals working in different roles. He doesn't usually stay on my lap that often. So now I can't even move properly. His name is Zai, Z-I-Z-I, that's his name. Okay, so there's the working location, right? They also look at working location. Again, these bars are point estimations, confidence intervals. From the size of the confidence intervals, you can almost figure out like the number of elements in the sample. And you can see that working from home is less likely to be infected than working outside of home, for example, right? And that's the interpretation of the findings. So again, I've shared with this you on the by symptoms, right? Showing any symptoms, not any symptoms. So showing symptoms is more likely to test positive than not showing symptoms. And of course, that makes intuitive sense. So there's a lot of data, a lot of findings in this particular survey that I've shared with you. If you're interested, you can take a look. And now you also know a little bit more about the statistics behind these surveys and how, not exactly the exact methods, but you understand what exactly do those whiskers mean, and you can also get a little bit insight into these whiskers Okay. So I'm going to go back to the PowerPoint slides. And we'll continue this lecture to the next topic. So now we can move on to test some hypotheses, and you will see that it's very similar to point estimation, but the logic goes a little bit further. So, for example, in the electoral pool, usually you want to test if there's 50% or more than 50% people will vote or not vote for someone. And based on a sample, we have 52.5% with a 95% confidence interval. So we can conclude that mu is actually larger than 50%. And now, but we are not attached a p-value to that conclusion saying p is smaller than 0.05. What this means is that there's a small probability that the result is due to sampling error instead of due to any true difference. Okay? Again, this p is smaller than 0.05 is that there's a small probability that is smaller than 0.05, smaller than 5% probability that the results, the conclusion, or the results that we obtained, that we had x bar equals 52.5%, right? This result is due to sampling error instead of the mean actually larger than 50%. What I'm saying is that the mean is actually 50%, but we obtained this result due to sampling error. And as I showed you earlier, every once in a while, sampling error happens. Just by simulation, 5 out of 100 times we get a estimation, a 95% of a confidence interval not covering the population mean. And that's sampling error. So today we're just going to go through quickly the very basics of hypothesis testing. So the very basics. And here are the results that you often see in news articles, right? It's all point estimation results. For example, you can, in 2017, survey shows more than 46% of Americans check their smartphones before going out of bed. And that has increased from 2016. Or the tech industry average time of sleep, 6.2 hours per night. And in the UK, the number is 6.7 hours. Again, just by the numbers of self, it seems to suggest that in the UK, people working in the tech industry sleep longer than in the US. But is that the case? And as children's self-esteem increases, they're less likely to give up when facing difficulties. And this is a categorical statement that doesn't even include any numbers, but just saying that there's some kind of a relationship between the two variables, and that's the direction of the relationship. So that's what you often read from news articles, but in research papers, you get more information about that. So, for example, you will see that there's a significant increase of percentage of Americans checking their smartphones, and they attached to it is a chi-square 1 equals some value, p smaller than 0.001%. You have a chi-square value and a p-value. And if you still remember the chi-square distribution that I showed you earlier, you probably get an intuitive sense of what exactly that means, because it's a very large chi-square, and larger values are more difficult to occur, right? It's less likely to happen. So in this case, it would say that the probability of chi-square being so large, given the degree of freedom of 1, is lower than 0.001%, which is 0.001, which is 0.1%. The same thing with a survey comparing the UK and the US tech industry average sleep time. Then in this case, you have a t-value, t equals 2.25, p smaller than 0.05. Okay? And if you remember t distribution, you can get the same kind of intuitive sense of what this means, is that the probability of t-value larger than 2.25, which is an extremely large value, is quite small. So the third one, you have R, indicates a correlation between these two variables, quantitative variables, that is children's self-esteem and likely to face difficulties. You have R equals 0.3 and P smaller than 0.005%, 0.005. This really, what it's saying that is that this R, the correlation is different from 0. Okay? That's what it says. And the probability of that, a probability of that they're not different from 0, 0.3 is not different from 0, is smaller than 0.5%. So the question is, what is a hypothesis testing? And you will see that it is connected very closely to sampling estimation and the probability that we studied in the previous lecture. What exactly is being tested and how did it actually test it? And what exactly is p-value? And that's really the most important question, and the question that a lot of even experienced researchers couldn't answer correctly. What does it mean to say that p is smaller than 0.05? It's not really complicated. It's just a lot of time people don't really think about exactly what p-value is. So there's some quick and simple answers is that what is hypothesis testing is that we're just assessing evidence provided by sample data, and we're assessing it in favor of or against some kind of claims about the population. So again, we're trying to draw a conclusion about the population. And in this case, the conclusions comes in the form of certain claims. What exactly being tested is test statistics. So the chi-square, T, R are all test statistics. And they comes with certain distributions that we already know. Okay? And based on the what we learned from distribution and probability, we know that once we have a value, we are able to get from the based on the distribution, how extreme or how unlikely are those test statistics, right? So basically it translates to how extreme or rare are these sample data that we actually obtain. What is p-value? P-value is basically how likely would the sample data happen given what we initially hypothesized about the population. So for example, if we, our initial hypothesis is there's 59% of registered voters who will vote for Trump, then p less than 0.05 means that what we observe from the data would happen on less than 5% of the time if this hypothesis is true. Okay? And based on this information, we can do something about the initial hypothesis. We can choose to reject it, or we can choose to not reject it, right? So let's get into some more specifics. The hypothesis testing involves 4 steps in particular. The first step is called state the null hypothesis and the alternative hypothesis. So by creating 2 exclusive hypotheses, we create a binary choice that we can decide. The second is we collect data from a random sample, and check the conditions and summarize using the test statistic. The third step is to access the evidence and find a p-value using the test statistic. Okay? And the fourth step is just based on p-value, we decide whether we have enough evidence or this evidence is strong enough to reject HO and accept HA, which H alternative. A stands for alternative, and we have to draw our conclusions in context. So let's illustrate these 4 steps with an example. So let's say we want to ask the question, is there a relationship between gender and SAT exam? If you heard about SAT, is the American exam that is required for university entry. So there's a following report. They're saying that in 2003, males scored higher than females on the SAT. So an education researcher wanted to check whether this was the case in her school district. So they draw a random sample of 100 males and 150 female students from the school district, okay, and get their SAT score. The first step is we want to state the hypothesis. The null hypothesis, right? The null hypothesis means that there's nothing happening, there's no difference, there's absence of relationship. In this case, the males and females are the same. So there's no difference, okay? Hence the null hypothesis. Now, what the alternative hypothesis in this case is that males scored higher on SAT than female, or you can say that performance is related to gender in a way that males gets an advantage. And then we'll collect data, right? So assuming that this is the data we collected, we're gonna skip research design for now, but we assume that sampling, we already know that we want a random sample of the male and female students in the district. So, so assuming that this is the data we have collected, so we have 150 male students and 150 female students. We observe that for the male students, the mean SAT score is 1,025 with standard deviation of 212. And for female, the mean is 1,010, standard deviation of 206. So that's now data collection, right? Now we have to assess the evidence in some way, right? So if the SAT scores are in fact not related to gender, how likely it is to get the data that we just got, right? So we translate that by basically subtract one mean with another mean, so get a difference between the means. So remember the difference between the means between the two means is 15, right? So what is it? 15? Yes, it's 15. 1,025 minus 1,010 is 15 points. So so now, how likely it is if we do a random sample from a population where there's no gender difference, right? How likely it is to get this particular data, that we have a mean difference of 15 and those two standard deviations that we are not showing here. So through a procedure called t-test, I'm going to talk about that later. So we found that the probability of observing this result is 29% if there is no gender difference. Okay. Again, if there's no gender difference, the probability of observing the data that we got here, which are this particular data with the exact n and mean and standard deviation, is 29%. So there's that much of a probability we're going to get this when there's actually no gender difference. Okay? Hope that's clear because that's quite important. So here now we have an example of observing a sample like this one we observed. It's not very surprising, right? So because 30% of chance is not very surprising if the null hypothesis were true. So therefore, we basically can conclude, because we decided that 30% is not surprising enough, that our data does not provide enough evidence for rejecting the null hypothesis. Okay? Now, the tricky bit is that this is not saying that the null hypothesis is true. It's just saying that the data is not strong enough to reject the null hypothesis, which is different from the statement that the null hypothesis is true. In fact, this data cannot speak of the strength of the null hypothesis. That's one serious drawback of this particular paradigm, is that if we fail to reject the null hypothesis, that's it. We don't really learn much from this conclusion. And we cannot conclude that the null hypothesis is true either. So there's no estimate this is not an estimate of the strength of null hypothesis. So we're going to go through each step in a little bit more detail. Okay? So the first of all is that we want to state the two hypotheses. We're basically making two opposing claims about what's going on in the population. Again, the hypothesis is something about a population. So the statement can be about the value of a population parameter, or about the existence of either difference between two groups, or a relationship between two variables in the population. The claim one is that nothing special is going on, right? So hasn't changed since 2019, right? It hasn't changed from 49% yet, or there's no gender difference in SAT performance. This indicates a null hypothesis about CQ relationship, if you still remember what that is, because gender is a categorical variable. Or if you do a survey to look at how conservatism correlates with sexism, then you have a QQ relationship. Then nothing special going on. It's just that conservativeness has nothing to do with sexism. But there's nothing going on. No relationship, no difference. Hasn't changed much. So the claim 2 indicate there's something is going on, such as the percentage of people voting for Trump has already changed from 2016. There is a gender difference. There is a difference between there's a relationship between conservativeness and sexism. So the claim 1 is called HO, not H0, but HO. Claim 2 is called HA, which is alternative hypothesis. So H stands for hypothesis. So yeah, I guess those two names are quite intuitive, right? The null versus alternative. So you can do some exercises what exactly the hypothesis is here. For example, according to the Center of Disease Control Prevention, the proportion of US adults age 25 or older who smoke is 0.22. So a research suspected in the younger population, if you have, is either lower among a US adults 25 or older. Okay, so older population who have a bachelor degree or higher education level, they will have a lower rate, right? So the null hypothesis here is that there is no difference between these two age groups or education groups, this particular group, and from the average, the US population. And the alternative hypothesis is that the rate is lower in this particular group compared to the US population, which we know is 0.22. So in this case, you're basically comparing a group with a known parameter, with a known population parameter here, right? So in this case, another data was collected to determine whether there is a relationship between the level of education and whether or not the person is a smoker, right? In this case, what will be the null hypothesis? And it basically saying that there is no relationship. So a person's level of education does not affect whether the person is a smoker or not. There's no relationship between the two variables. An alternative hypothesis is that there is a relationship between these two variables. And in step 2, we call it check conditions, summarize data using the test statistics. So we have skipped the data collection part, assuming that we already have the data collected, right? So summarize the data. We can use, for example, we can use a simple sample statistics, right, to summarize the data as a sample mean X bar, standard deviation SD. And if you have two groups, you can have two sample means, right, X1 and X2. But now we'll go a step further to convert the sample statistics onto a test statistic, okay? Which means Z score, chi-square score, t-score, F value. Right? Now, different types of data relationships will require different test statistics. So, that's the first thing, right? You remember that in order to, the most important things to look at is what type of data or what type of independent variable and dependent variable there are. And now we know that this is important because not only it depicts, it dictates how we depict their relationship in the exploratory data analysis, but also dictates the type of statistics test that will be used to test the relationship. Also, we need to check that certain conditions has been met in order to use certain test statistics. such as conditions about independence, conditions about distribution of the variables, and conditions about variation. We'll go to these specifics in the next lecture. We're not going to those specifics now. And you will see that sometimes certain tests are robust even if some of the conditions have been violated. So they are, even if the conditions are violated, you can still use certain tests for some of the tests. Now, I will also not go into details about how those sampling statistics are converted into test statistics, right? How do we convert a sample mean into a Z-score? But you pretty much get the idea of that because we already calculated the Z-score before. We know that we have to convert a mean score into a Z-score if we know the sample mean, the population mean, and the standard error. Okay, so we kind of get an idea how it was done for the Z-score, but for some of the other scores here, like chi-square and T and F, we haven't gone into that yet. So here's the step 2, right? So step 2 turned into a test statistics, and now step 3 is just to find a p-value. Again, a p-value, again, is just basically how likely it is to observe this data if null hypothesis is true. That's very important. So that's the most important bit, and that people forget, is that p-value indicate how likely it is to get the data if the null hypothesis is true. So there's a premise there, right? And some of you mentioned statistical power before. Statistical power applies to the condition when null hypothesis is false. Okay, and null hypothesis cannot be true and false at the same time. Okay, so you can see that the p-value and the power, they are two different concepts, and because they operate under they have different premises, right? So p-value represents the probability. Okay, and it takes value from 0 to 1. Again, if that sounds familiar, that's about right. And closer to 1 means smaller, close to 1 means larger. But again, p-value indicates how likely it is to get this result, right? If null hypothesis is true. So we decided that the smaller the p-value, right, the more evidence the data presents against null hypothesis, which means that the less likely it is to observe the data if the null hypothesis is true. So a very small p indicates the results are very surprising if null hypothesis is true. P equals 0.2 indicates that if null hypothesis is true, there's a 2% of likelihood of getting the data observed. Then we should tend to reject the null hypothesis, right? On the other hand, if a p-value is not very small, 25%, then it means that observing data like that is not very surprising if null hypothesis were true. So the data does not provide evidence against null hypothesis. We cannot reject the null hypothesis. So let's look at how an example of how this is interpreted. So there are two hypotheses. If we want to test the proportion of voters who oppose Trump, is either 50%, that's the null hypothesis, right? If you choose like the chance value, if you choose chance as the null hypothesis, then it's 50%. That's the safest bet, right? And also that determines, well, not in the US, but that basically determines the outcome of the general election. So and the alternative hypothesis is it will be higher than 50%. So we do a survey with a random sample of 1,100 US adults. We found a p-value of 0.002. So what exactly does this mean here? A, there's 0.002 probability of observing data like those observed. B, there's this probability that 50% of adults oppose Trump, 50% of adults oppose Trump. C, there's this probability to observe data like those if the proportion who oppose Trump were 50%. D, there's 99.8%, which is 1 minus 0.002, that the majority of US adults oppose Trump. So give me the answer in chat if you. Is it A, B, C, or D? Quickly pause recording. Notice that it doesn't mean that there's 99.8% probability that the majority of US adults oppose Trump. Okay? It only says that the likelihood to observe this data, if the null hypothesis is true, is 0.2%. Okay? So, which means that 1 minus p-value, 1 minus p-value does not indicate, how do I say, that the probability of the alternative hypothesis is true. Okay? So remember, this is how strictly the p-value is interpreted. And then you will have to, I'll come to that later in the next lecture. But I think it would be helpful to go back to the simulation we saw earlier to understand exactly what is the p-value, if that's okay. And this is improvised, so bear with me. So going back to the original, to that. Okay, so if I share this with you. So this is a confidence interval simulator, but so this is a confidence interval simulator, right? But we could use it for the p-value to demonstrate what exactly p-value is. So in this case, let's say the null hypothesis basically mu is mu. So there's no, it's not, the mu is not there or there. The mu is like here, right? So we know that most of the times, if we do sampling, we get results that are covering mu, which means that these sample means will not estimate, based on these sample estimates. Remember, these sample means are estimates of the mu. So basically what it's saying that I'm estimating this one, the first one, I'm estimating this population mean is here, right? So now the question is does it suggest that there's a new, the population is like, is to the left? Or is it strong enough to say that, is the evidence strong enough to say that the population that we're estimating is different from this mu, right? So once in a while, we get very unlikely results, right? But most of the time, we are getting the results we're getting suggest that it's not different from mu, right? So the p-value is basically the probability of how likely it is that we are actually sampling from mu, not from a different population, but we still get what looks like there's a difference, okay? So for example, sometimes by sampling error, but just by chance, there's a small likelihood that we're getting some estimates, getting this data. So instead of indicating a true difference that this population mean is different from mu, what we are actually getting is, in the results, is sampling error. Okay, so p-value is basically the probability that our results is due to sampling error if the null hypothesis is true. Okay? I know that might actually sounds confusing, which is totally fine. We're going to come back to this in the next lecture again. Okay? But again, just repeat it that the p-value is the probability that we get this finding if the null hypothesis is true. Okay, it is also the probability that what we get is due to sampling error if the null hypothesis is true. So eventually we're going to make a decision about rejecting the null hypothesis or not. So if we have a very small p-value, then we will reject it and we will accept the alternative hypothesis, which says that there is actually a difference, or the population is different from the population specified in the null hypothesis. So how small is, but if the p-value is large, then we can't reject it. But we still have to decide how small is small enough, which means that we need some kind of threshold for our decision. And usually this threshold is called significance level. It's also called alpha. Remember earlier in the Excel equation, there's an argument set alpha. So usually most common used alpha level is 0.05 or 5%. Which means that if p is less than this cutoff value, right? If the probability of obtaining this data, if the null hypothesis is true, is very small, is less than 5%, we say that the data provides significant evidence against the null hypothesis. So we reject the null hypothesis and accept the alternative hypothesis. Hold on for a second because the cat wants to go out. I'm going to let him go out. Okay, you can go out. There you go. Let's just hope that he doesn't want to come back in again. And if the p is larger than that, we say that this data does not provide enough evidence to reject the null hypothesis. Okay? And this whole paradigm is called null hypothesis significance testing. It is the most commonly used paradigm in empirical science. It has its pros and cons, but the fact that it's being used very widely and popularly indicates that it's a very influential paradigm. And recently, there's alternative paradigms, such as Bayesian tests, Bayesian statistics, that are getting more and more popular. And so we'll discuss these criticisms to this paradigm next lecture. We'll also illustrate more specifically what does it mean by saying that the population, the null hypothesis is false. The alternative hypothesis, because I didn't really represent the alternative hypothesis in graphics in this particular lecture. So that's it, everyone. I will share these slides in the space, in the shared lecture space. And the next lecture will continue to talk about hypothesis testing. Okay, I'm going to stop recording.